light-driven micro-robots and micro-machines based on optoelectronic tweezers. So without further ado, let's welcome Professor Zhang to share his research. Please go ahead, Professor.
My first question for you, can you see my changing my screen?
Yeah.
Okay. Okay, hi everyone. My name is Shuailong Zhang. I'm currently a professor working at the School of Mechatronic Engineering, Beijing Institute of Technology, and also Beijing Advanced Innovation Center for Intelligent Robots and Systems. I feel really honored today to be invited to give a talk here. And the title of my presentation is Light-Driven Micro-Robots and Micro-Machines based on optoelectronic tweezers. First, I would like to introduce my previous group at University of Toronto because all of my research was done at Toronto based at Professor Aaron Wheeler's group. Professor Aaron Wheeler is a Tier 1 Canada Research Chair and currently the chief editor of a flagship journal of microfluidics, Lab on a Chip. And the group is based at the Institute of Biomedical Engineering and Department of Chemistry at University of Toronto. And the research topics cover lab on chip device for diagnostics, digital microfluidics, point-of-care diagnostics, biochemical assay, and optical micromanipulation technologies. So just a quick question, can you hear me?
Yeah, we can hear you.
Okay, thank you. And a little bit background introduction. And the 2018 Nobel Prize, a share of it was awarded to Ash Askin for the invention of optical tweezers and their applications. So for my work, I use optoelectronic tweezers, which is a related technology that uses light-induced electric physics force for the manipulation of microparticles. So basically, I use light to trigger electrical field, and use the field to interact with microparticles through dielectric physics force. As you can see in the video, by shining the light pattern or using a movable light pattern, I can assemble microparticles, or I can use it to rotate and move microparticles. And these microparticles can be polystyrene beads, or can be cells, or can be some metallic beads. So here is a video showing I use light pattern to move 10 micron size polystyrene microbeads. So how does the device work? So in optoelectronic tweezer device, we use light to generate this non-uniform electrical field. So our device consists of two plates, both of them ITO coated glass. ITO is a transparent conductor, but at the bottom plate, there's an additional layer of amorphous silicon, which is a photoconductive layer widely used in solar cells. So it is coated on top of the ITO. So if we apply the electrical field between two ITO plates, there will be uniform electrical field across the two plates, similar to a parallel capacitor. However, if we shine light to the photoconductive layer, the photoconductive layer absorbs light and convert it into hole and electron pairs. In this case, its conductivity drops. And in the system, this will trigger non-uniform electrical field. And if this non-uniform electrical field interact with the particles, it will generate dielectric physics force. And if we move this light, we will move this non-uniform electrical field. Then we will move the particles that interact with this non-uniform electrical field. And here are the devices, what are the devices look like? You can see the top plate is basically transparent because it's ITO coated glass. And the bottom plate is a little bit darker because it consists of a thin layer of amorphous silicon. Here is what the video looks like. So I can use dynamic light pattern to move and rotate 10 micron diameter polystyrene microbeads. So you can see different from optical tweezers. So in optoelectronic tweezers, I use light pattern instead of discrete laser spot to control and move micro-sized objects. So here is using a static light pattern to massively assemble hundreds and thousands of microparticles. So you can see these microparticles assembled into a picture featuring Marie Curie and symbol of radiation. So after introducing the background, I'd like to go to the topic of light-driven micro-robot. So probably you have seen the examples of light-driven micro-robot. So for the past 10 years, so researchers in this field, they develop all kinds of micro tools or micro robots or micro machines that can be controlled and manipulated by optical tweezers. So as you can see here are examples of using optical tweezer to control probe to scan the surface of a tumor, and as a surface profilometer to scan the surface of micro objects, or use it as optical tweezers to control micro car or micro vehicle to deliver and transport secondary objects. And of course, as shown in the bottom right picture, people use optical tweezers to rotate microparticles to generate vortex, which can function as pump in the microfluidic channel. However, for optical tweezers, the problems, as you can see in these examples, the objects they can control are quite small. This is a fundamental limit of optical tweezers because it cannot operate relatively large objects. Well, in my work, I developed all kinds of robots with sizes of hundreds of microns. These robots can be gear-shaped micro robot, box-shaped micro robot, or space-shaped micro robot, as shown in the SEM images. And I simply use light pattern to match the layout of the micro robot to provide driving force. And as you can see here, these robots have very unique properties with large artificial micro tools, and their mechanical structures can be easily redesigned, and the optical control system can be easily adjusted to provide the driving force. Here is an example of using robot as a micro carrier. So the process is that I use a micro robot and to load a micro particle or payload, transport it, and deliver it. So here is a video showing how I rotate the robot, use it to catch microparticles, and then deliver it to a specific place. So maybe you will have a question for me. Since you can directly using the light pattern to control the microparticle, why you want to use the robot to engulf the microparticle and then move it? So because experimental results suggest, compared with directly using the light pattern, the micro robot exerts stronger manipulation force and allowing the payload to have a higher linear velocity in the optoelectronic tweezer system. Here are some examples of parallel control. Because when we talk about micro robotic system, we always want to control parallel or multiple micro robots simultaneously or multitasking applications. So as you can see here, by controlling multiple light patterns, I can control multiple robots simultaneously with different payloads inside. So compared with optical tweezers, I just use light pattern. So it's much easier to implement compared with optical tweezer, which use laser system. And here is an animation showing how I can use light driven micro robot for cell manipulation. So here are some results of using micro robot for cell manipulation. I can use micro robot to catch different cells to form controlled cell mixtures. And it's found that if I use micro robot, it can exert stronger manipulation force and allow the cell to have a higher moving velocity. And cell also has higher cell mobility in the system, which is due to different mechanism and dielectric phrases and fluidic pressure. So when cells are directly manipulated by light, light can bring heat and can bring electrical field, which can hurt the cell. But if you use the micro robot, the robot can confine the cell in the central region and keep the cells stay far away from the dangerous zone, which can hurt the cell. In this way, the cell have a higher cell mobility. And here are some examples of using micro robot to catch and deliver cell from cell mixture to a microwell and then I can perform cell culture, and the cell can do a colonal expansion. So the system is fully compatible with cell, and it also show very good biocompatibility. Another example is that I can use this robot to select and isolate precious payloads from heterogeneous mixtures. For example, I can use micro robot to navigate through a maze of debris to collect neurospheres from primary mouse brain dissections. So neurospheres are 100 micron diameter, free-floating multi-cell colonies comprising neural stem cell and their progeny. And neurospheres are very useful for regenerative medicine and treatment. And here are examples show how I use a micro robot to sneak in to a maze of debris and to extract neurosphere. So here is a summary of the work. So the light-driven micro robot based on optoelectronic tweezers was developed. So these micro robots are easy to fabricate, easy to operate, and they can be parallel controlled and manipulated. So I provide an indirect manipulation tool for microparticles and cells, and this system can provide stronger manipulation force with light harm to the cells. So our future work in this area is try to upgrade the system with artificial intelligence algorithm so that system can perform automatic identification of the cell and path planning and control the micro robot to harvest the cell. And I hope in the future, the system can do the cell selection process all automatically. So of course, based on this work, my research group at the University of Toronto received a prestigious grant of 1.6 million Canadian dollar in total to work with AI scientists at the University of College London, UK, to develop a micro-robotic system for automatic neural stem cell extraction and analysis. So here comes second part of the work, light-driven multi-component micro-machines. So as I showed previously, so I can control micro-robot. So the question is how I can utilize parallel control of multi-component or multiple micro-machines at the same time. As you can see in the picture, I use microgear as basic unit, and the microgears similar to the micro robots. They were fabricated using SU8 materials and photolithography, and the system support parallel control and manipulation. Here are some examples of using light pattern to control a single microgear or control 9 microgears simultaneously. As you can see here, by applying different light patterns, I can put the gear into an array and to trap them and to rotate them simultaneously and at different angular velocity and different rotation, which can be clockwise or counterclockwise. And also, I also studied some hydrodynamic, did some hydrodynamic study on this rotating microgear, and it's found that to study the influence of the rotational micromotor on nearby particles. And I found that this vortex generator can impose hydrodynamic force on nearby particles and also run some neural simulations to support experimental results. Here are some examples of using a rotating microgear to control 1 micron microbeads. As you can see, the microbeads start to move around this rotating microgear, and definitely vortex flow has been created using this rotating micromotor. Of course, I can use this rotating microgear to move 15 micron size polystyrene microbeads. And also, as you can see in this video, a microbead can is moving around a revolving microgear. So by control the speed of the rotational microgear, by controlling its angular velocity, I can control the moving speed of the microparticle. So this is more like an indirect manipulation of the microparticle through hydrodynamic. And of course, by using multiple micro gear, use a pair of micro gear as micro feed roller, I can control the movement of microparticles to accelerate it. And also, if I use OET bridged micro feed roller, I can combine the force from the lat pattern together with the fluidic force from the rotating micro gear, which can provide stronger force for cell. And together with specific lat pattern and with the rotating micro gear, I also can utilize the vertical DP force to lift the microparticles and use the fluidic flow to push the microparticles forward. In this case, I can achieve 3D control of the microparticle to make it cross over 3D structures or jump into a 3D microplateau. Here are some examples of using micro feed roller to accelerate a micro bead. As you can see, the bead start to move and its moving velocity start to increase in the middle of the rotating gears. And also using the OET bridge touchless micro feed roller, I can combine the force from the lat pattern with this rotating micro gear, and the cell can be moved at a much higher speed compared with using a lat pattern alone. So I also fabricated these SU8-based 3D microstructures, which are fixed structures in OET device. So they have a height about 60 microns. Sorry. Okay, so here is a video showing how microparticle cannot cross over 3D structures by OET alone. But using OET bridge touchless micro roller, microparticle is made to move forward and hop over 3D structures. So this kind of movement is like shooting a basketball or launching a rocket. You can see the microparticle can jump over 3D structures or jump onto the top of 3D structures. So I also studied a micro gear trains based on the system. So as you can see here, I demonstrate versatile optoelectronic gear trains consisting of active motors and passive motors. And these multi-component micro machines made of different combinations of micro gears. And the advantage is its flexibility and programmability. So the system is fully reconfigurable. As you can see here, I can use a micro gear train comprising one active micro gear and one passive gear. So I use a lat pattern to drive an active gear, and then I use this active gear to drive a passive gear. So the system is capable of pass the mechanical energy from one gear to another one. And of course, micro gear trains can be consist of gears with different sizes. So here I fabricate 150 micron and 300 micron diameter microgears. And as you can see here, the mechanical system with different mechanical advantages because using different gears. So here I'm using a smaller gear to drive a large gear. So this one, the system can give a higher torque. So this is torque amplifier. If I'm using a large gear to drive a small gear, so this one can give it a higher velocity. So it can be a velocity amplifier. Another thing I demonstrate is rack and pinion system. So rack and pinion is a very important mechanical structure that can convert rotation into a linear movement. Maybe you see the gate of a castle, so it utilizes a rack and pinion system, and also stereo view also utilize rack and pinion system. So here I fabricate a micro rack and pinion system that can convert rotation into linear movement in the micro scale. And also I can use micro and pinion system together with microfluidic structures and use them as microfluidic walls. So the micro pinion systems can move and can be selectively moved to open and close microfluidic channels. In this case, it functions as microfluidic walls. And here are some ICM images showing the mechanical structures of the rack and pinion structures and the microfluidic structures. So it's all integrated in the microfluidic channel. Here is a video showing how the micro rack and pinion in operation. So can you see the video?
Yeah.
And as you can see in the video, I also can achieve parallel control of rack and pinion system so that they can work simultaneously to form a microfluidic wall. So this is open the channel. Here is a summary of the work. So I showed light-driven multi-component micromachines based on optoelectronic tweezers. So the system are easy to fabricate, easy to operate, and support parallel control and manipulation. So it's an indirect manipulation method using vortex flow, and the system is fully reconfigurable and transformable, as shown by the gear train system. And also the system is multifunctions. I demonstrate microfeed roller for 3D control of particles, gear trains with different formats, and micro rack and pinion system that can be used as microfluidic walls. And the paper is published in Nature Communications last month. Finally, I want to talk about the commercialization of the technology. I think most of the people here are researchers, and we work on optical micromanipulation of nanomotors or micromotors. So I think it's important one day that we can commercialize this technology and use it for improve the lives of human beings. So here is a great example of how the technology can be commercialized and getting really successful in the market. So here is a very interesting academic tree that I want to show you. So the optoelectronic tweezer technology was invented by Professor Ming Wu and Eric Otta back in 2005. So they published and also Eric Chu and they published the paper in Nature in 2005. And my PhD supervisor, Steve Neal, he is a postdoc with Professor Ming Wu at UC Berkeley. Now he brings the technology to UK, where I did my PhD with him. And after that, I joined Professor Aaron Wheeler's group at the University of Toronto. And Professor Aaron Wheeler is a friend of Aaron Alta and Professor Ming Wu, because they used to work together at UCLA back in 2003. And he knows the technology pretty well, and he supports me. So that's why I have the chance to work in the field of optoelectronic tweezers for the past 6-7 years. So at Professor Ming Wu, I call him the father of optoelectronic tweezers, or the inventor of optoelectronic tweezers twice. So once in his lab at UC Berkeley, another one at a conference in Tucson in Arizona in the States. So he's the founder of Berkeley Lights, and Berkeley Lights went to IPO on NASDAQ last year, and the company is now valued at $4 billion US. And the big shareholders, including RKTF, GenFund, and Alibaba. And Berkeley Light is a biotechnology, is a biotech company that, but with its core technology as optoelectronic tweezers. So they developed two platforms. One is called Beacon, another one is called Lightning, and both systems use microfluidic devices together with optoelectronic tweezer function for cell biology applications, such as cell line development, cell therapy development, antibody discovery, and synthetic biology. So here is the workflow of Beacon. So first, they load the cell to the microfluidic channel, then they use the light pattern and optoelectronic tweezers to move the cells to the microvials. As you can see here, there are hundreds of thousands of microvials in the microfluidic channel. And after that, they can control the temperature, provide CO2 and humidity, and to make the cell to grow, adhere, and perform clonal expansion. Then they can put all kinds of fluorescent probes, or fluorescent antibodies, or fluorescent indicators to find the cell with the correct function, or cell with specific phenotype. And after they find the best cell, the cell with the functions, they can export the cell and to grow the cell in the well plate, or they can do sequencing and to link the genotype with the phenotype. So here is their workflow. So their slogan is that they can find the best cell, the cell with the best functions. Here is a video showing their platform, which I think is very interesting, and I would like to share it with you. Okay, I think that's the end of my presentation, and I would like to acknowledge support from Professor Aaron Wheeler and the whole Wheeler group, and also my collaborators from Peter Lenstra's group, Moshai's group, and Karani group at the University of Toronto, and also my international collaborators at the University of Glasgow and Sun Yat-sen University. Thank you for listening, and I'm happy to answer your questions.
Okay, thank you, Professor Zhang. Thank you for your wonderful talk. Let's say if we have question or comments from the audience.